Hello, everybody. Welcome back. It's Alex Does Lead Code. It's that time of week again, and it's time to do programming problems together with me on stream. My name is Alex, and as usual, the best way to learn from this channel is to try out these problems on your own before the lesson or during the live stream. Whip out a laptop and work on it yourself. But if you can't do that, then just follow along with me. Bring your attention span, focus, and let's get started. Today's problem is number 30, substring with concatenation of all words. And this is a very long problem, as we talked about last time. Let's read through the problem description a little bit and see what's going on here. Alright, it says here, you are given a string S and an array of strings words. All the strings of words are of the same length. Okay, you know what? This is very long. A concatenated substring in S is a substring that contains all the strings of any permutation of words concatenated. Okay, so basically you're given a string S and an array of words. Okay, so you have words that look like this. They're not actual words, they're just strings. And they're all the same length. So this thing would actually be this part would actually be important later on. And so you can concatenate them in some way. Any permutation. Okay, so all these permutations contain every single word in some order, right? A, B, C, D, E, F, A, B, E, F, C, D. So A, B, E, F, C, D. So they use all three. But because it says any permutation, I believe that it does not have to contain all of these strings. Okay. It's not a concatenated substring because it's not a concatenation. So A, C, D, B, E, F. It's the same letters, but AC does not appear. AC is not a word here. AB is a word. There's an AB, but there's no AC. Okay, return the index of all concatenated substrings in S. So, for instance, if S is bar stool the foot bar man, the foo bar man, and the words are foo bar, you have 0 and you have 9. 0 because it says bar foo. Okay, gotcha. And then foo bar is 9. Since words.length equals 2 and words I.length equals 3, the concatenated substring has to be of length 6. Okay, I see. Okay. So I was wrong about this. So it looks like the concatenated substring has to be any permutation, not any combination. It has to be any permutation, which means it has to use all three. It has to use all three. So bar foo is a concatenated substring, but foo itself is not, because you need both foo and bar. You need to use every single word in the words array. It's the concatenation of bar and foo, which is a permutation of words. The substring starting at 9 is foo bar. It's a concatenation of foo and bar, which is permutation of words. The order does not matter. Returning 9, 0 is fine too. Okay, let's see. Let's think about how we want to do this. Okay. What about... Okay, let me clarify the problem a little bit. What about bar foo bar? Okay, bar foo bar the foo bar man. Oh man. Word good best word. Word good best word. Since words not length and length, there's no substring of length 16. Okay, so word good best word. This would return nothing. Because even though all of these words appear in the string, they don't appear all at one go as a single concatenated substring. They do not appear as a single concatenated string. So word, good, 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 best word. So there's word in front, best word, but there are a bunch of goods in the middle. So there's good, best word. There's no word, good, best. Word, good, best word. And you have to use both words. I see. So you have to use both words. So good, best word is not a concatenated substring. It's not a concatenated string. Okay. Wow. Whew. This is quite a slog. Okay. Ba fu fu ba the fu ba man. Ba fu the fu ba. You have this, the fu ba. You have ba fu the fu ba the. Okay. So 6. Wait, 6, 9, and 12. 6. Okay. Yeah. Fu ba the. Okay. That's 6. Well, 9. Ba the fu. Okay. That too. And the fu ba. Oh, okay. So the concatenated substrings can overlap. Yeah, that was the question I had. So ba fu ba will return both. Okay, if the input is ba and fu, then ba fu ba will return both 0 because of this, and then fu ba, and then return both 0 and 3. I see. So this is a fairly complicated problem, as I talked about last time. I'm normally not a fan of these problems. I'm just gonna try it out and see how much pedagogical value we can get out of this. Working on this together today, but unfortunately, many company, when they give their tech interviews, they sometimes, I don't like it, but it happens. They sometimes will toss these kinds of problems at you. So I want to go through these at least a couple times so that we can get all of you prepared for whatever that might come your way. Okay, so without further ado, let's get to how we want to tackle this. So here's what I'm thinking. Okay, you have a list of words and you have a string, and you want to know if the words appear in the string, right? So the first thing I'm gonna do is I'm gonna look for all occurrences of all the words in the string. This is a little bit tricky. This is actually a little bit tricky because so the first thing that comes to my mind is you want to look for fu ba, right? Well, let's let's take this for example. Ba fu the fu ba man. I'm hating the names already. You have is this a highlighter? Do I have a highlighter? Yes, I have a highlighter. You have ba, and then you have fu. And the idea is we want to highlight, quote unquote highlight, each of the substrings that we have, right? I think this is slightly better than going to the string character at a time and checking, is this part of a word, is that part of a word. That gets annoying very, very quickly. So instead, what I want to do is we want to find out, let's start by doing this. Let's start by collecting all for each word in words, we're gonna find all the occurrences of that word in the string. Okay. So that's going to be our first step. Okay, so already I can think of a few tricky problems. Okay, so in this case, it's actually not hard. If we're only talking about this case, it's actually not hard. All we have to do is to find all the occurrences of fu, all the occurrences of ba, and then look for places where they are sort of like the indexes match each other. So what I'm talking about, if this is 0, the next one should be a 3. notice that all the words are the same length. So if we want a permutation, we will have to basically find a sequence. We have to find a sequence that is length away from each other. So taking this as an example, okay, this is what I'm thinking of right now, and this might change as we go along. There might be better ways of doing this. So I'm gonna first find where each of these words occur. So fu will occur at 0, 1, 2, 3. So it occurs at 3, 6, and 9. So it occurs at 3 and 9, right? There's a fu here at 3, and another fu here at 9. Ba appears at 0, so this bar right at the front. 0, 3, oh god. And it appears at 12. This bar right here. Okay? So based on this, we will therefore say, and then length is going to be the length of words, since all the words are the same length. So length is going to be 3. So what we want to do is look for a sequence. We want to look for a sequence. So we look for a sequence. Actually, once we have this, we can throw this thing away. We don't need this anymore. We just need these indices, and we work with numbers. And we don't have to work with the unwieldy string, which I'm rarely a fan of. So we want to look for a sequence that contains all the words, and the indices are length apart, i.e. 0, 3. So this 0 and this 3 is a sequence. And this 0 and this 3 basically forms the concatenated substring. And this is kind of weird because we've taken out all the letters. We've taken out, we're taking out the entire strings from our problem. We're not dealing with strings anymore. We're just dealing with indices. And the reason why I do this is I believe it's easier to do it this way. Let's see if that's actually true. So just to be clear, I'm talking about this 3 and this 0. Okay, so 0, 3, that's a sequence. What's the other sequence? The other sequence is this 9 here and this 12 is a sequence. The reason why they're sequence is the indices are length units apart. So length is 3. So 9, 12. Why do they need to be length units apart? So that we know that, let's say there's a fu at 9 and there's a bar at 12. It tells me that fu bar is a word. If this were, say, 11, then it will be like this. That's not going to work. Similarly, if this is like 13, like this, fu x bar, then fu x bar is not a word. So we need to check that the sequences are length 3 apart. Yeah, so that's pretty much it. That's pretty much it. So how do you do this? Well, I would say brute force, maybe. Let's see. Well, these things are sorted, right? These things are sorted. So maybe what I'll do is to find the smallest number here, and then I'll add 3 to it, and I will see if there is a something that starts with 3. Yeah, let's try it out. I think we got it. Okay, so there is a degenerate example, right? There are a few weird examples. So while I'm thinking of the strategy, I'm thinking of the weird examples. So the way I think about programming is that we want to solve the easy problem first. Want to solve the easy problem first, and then we think about the corner cases. Because once we bring in a bunch of corner cases, then things get murky. This doesn't mean that the easy problem can be adapted to solve. The easy solution can be adapted to solve the corner cases. Maybe sometimes we have to throw the whole thing away and restart from scratch. But that's fine, right? Just doing it once first give us a good intuition for what we're supposed to do. Right? There's an old adage that says write everything twice. Just first one is a throwaway. Just refactor it later on once you got it. I think it was Martin Fowler who said that. Martin Fowler, who is a great programmer. Okay, so I'm thinking of a few sort of edge cases. I can think of at least 2 edge cases. And I'm not going to deal with them first. I'm just going to keep them at the back of my mind. The first edge case is exactly this one. Ba Fu the Fu Ba Man. Oh no, this one. Yeah, good, best word. So, words is ba, and then the string is like ba fu ba. So you, how would this work? Let me just quickly see this. I said I'm not gonna solve this, but let's see. This would be 3, and then bar will be 0 and 6. Yeah, actually this still works. So you see 0, you say, oh, there's a 3 here, so 0 and 3 combine, you can get that, and then 3 and 6 can combine later. So the other edge case, okay, I see. I'm getting hang of it. Okay, let's deal with the other edge case. Is actually when these words overlap. So for instance, so this is very annoying. So there's ba fu, and let's say this is fu fu ba. So you have fu fu ba, and then you have ba fu fu. Right? These are the 2 solutions. In this case, because these guys overlap, you get really weird cases where they have the same index. So fu will be 0, 3, and 9. Right? And fu ba will be 3. This is so weird. This is really weird to me because this word is entirely contained within the other word. This is like an edge case. Edge case 2. Word is contained within or overlaps another word. Okay, I don't think this would come into play. Okay, I don't know if the edge cases come into play, but let's solve the default problem first. So we're words, right? We have words. 4 word in words. So the first thing we want to do is construct the, let's call it the occurrence. Let's just call it occurrences. So occurrences is going to be a dictionary. Okay, for each word in words, we're gonna say occurrences, and okay, the other weird, annoying case is that these things can actually appear multiple times. But we'll deal with that later. We'll deal with that. We'll cross that bridge when it comes. Occurrences word equals to, okay, so we want to get all occurrences of word in a string. I think there is a Pythonic way to do this. Python all substrings in a string. I think there's a, yeah, rfind all. Yeah, this is the one. Oh, is there something like rfind all? There's no simple built-in function. Ah, goddamn. But we can use a powerful regular expression. Yeah, so we can do this. Let's not do it that way though. Let's do it what I would consider the sort of quote unquote proper way. So what we're gonna do is we're gonna say what I like to do actually is to declare this as a write this as a separate function. Okay, so what I'm gonna do is we're gonna call it find all. We have string s and then substring, and then find all returns a list containing all occurrences of substr in stir. And I think you can use a find, right? String.find. String find. Today is going to be both a treat and a bit of a slog. I think it's a slog because it takes a bit longer, but it's a treat because I think this is the first time we are dealing with a slightly more substantial problem. Okay, start end. Okay, so we're gonna do stir.find. Let me see if I can explain the logic here a little bit. Stir.find substring. Index equals to stir.find substring. Okay? What happens if you don't find it? Returns -1. Okay, cool. Index equals stir.find substring. Result equals to return result. And we're gonna concatenate things into results and then return them. Okay? So index equals if index larger or equals to 0, i.e. index is not -1. So it occurs, then we want to say result dot append idx. Okay, so what we're doing here is we're going to find the first one if index is larger than 0. Okay, we found substr in stir. You know what? I don't know if you can use s. Let's do s instead. So substr in s. Then we add the index to result. Okay. But because there are multiple copies, there are potentially multiple copies of substr in s, we put this in a while loop. I'm going to start with a while loop that looks like this first, and then I'll iterate to make this a bit faster. And so the way find works is you can pass it at index. We can pass it the previous index, prev idx equals to 0. It starts at 0 first. After we find it, we append idx to the result. We set prev idx equals to idx. And then we go again. It just keeps running. It just keeps running until idx is -1, aka we can't, in other words, we can't find it, in which case we break and we return result. Each time we start looking for one more than the previous index. So previous index plus 1. Okay, cool. So this is one way of doing it. There's actually an even shorter way. I am going to write it out here. Okay, so this is the way we're going to find all occurrences of substr in S. We do a while loop that runs forever. We say idx equals s dot find subster previous index. Okay, the previous index starts from 0. Okay, and each time we set previous index is to the last one we found, and we increment it by 1, and we find the next occurrence of subster starting from previous index plus 1. You can actually simplify this a little bit. You can actually simplify this whole thing by doing a few things. One is you can say that idx equals to 0, while idx not equals to -1. Dot append idx. You can make this a little bit easier by doing this. Okay, so this also works. This is what I would write if I were writing a production code. It's basically the same idea. You start saying idx equals to stir.find. If this is, while this is not -1, plus 1. So you start searching for you start searching from the beginning, and then while idx, you append it and you find the next one. And so both of them should work. I actually prefer this one in production code, but I prefer this one when I'm teaching, because this makes it a little bit easier to explain. Okay, cool. We spent a lot of time dealing with this find function. Let's hide it. Now that we're done with it, let's hide it. Let's just call it this is find stir 2. Let's hide it. I like hiding my code when I'm done with them. Okay, so I am going to do now find all s word. Okay, I want to point out one other choice that I'm making right here. That is to make find all a function. So I'm gonna bet dollars to donuts that if I did this with my students, a lot of people will write find all here. They'll do like, idx equals to s dot find blah 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 blah, right? Wow, blah 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 blah. They'll put this here. I actually don't like that. I don't like that because I think that you should organize your functions, your code into logical pieces. If you have a function, if you have a piece of code, you have a piece of logic that is intuitively separate from the main code, then we should put it out. We should take it out and put it into a function. So this idea of finding substrings in words is a very standalone idea and has nothing to do with this concatenated permutation stuff that we're trying to solve. So finding all substrings in a word is a very standalone idea. You can explain that idea without this larger context of the problem that we're solving. Because that's true, I like to take this and put this in a separate function. It also makes your code a little bit more readable. And in the future, there's more chance of making it reusable. But readability is the main thing I'm going for. Okay, cool. So now that I have this, I built this array here. Okay. This. Now that I built this dictionary here, actually I may not need a dictionary, but I'll figure it out later. I don't think I actually need a dictionary. I need a list of arrays, list of lists. But I'll figure it out later. So length is the only reason why I made this a dictionary is so that it's easier to debug. It's easier to debug. If you can make this a list, and then you would get a list that looks like 3, 9, 0, 12. Then this is a nightmare to debug. Whereas a dictionary has the words, so it's easier to see what's happening. This is harder to see. Okay. Length of words 0. Okay, we're gonna assume that there's at least one word in words. If there isn't, then well, sucks to be you or me. Okay, cool. So now that we have the occurrence dictionary, we're gonna look for a sequence that contains all the words. All the indices are length apart. Okay, give me a second. Okay. What am I doing? Hold on, I'm messing my stream a little bit. Okay, cool. So now that we have the first part is step 1 is create the occurrence dictionary. So we've done that. Step 2 is actually use occurrence dictionary, and this is how we're going to use it. Basically, we are going to find the next thing in the occurrence dictionary. So for instance, we're going to start from here because they are all sorted, right? Because this find all will give you the indexes in ascending order. We are going to find start with the smallest one, which is bar. We're going to start from the smallest one, and we are going to check. Okay, so first thing is find smallest index in the dictionary. And what I mean by smallest index is we're going to look for the smallest. We're literally going to look at the smallest number we haven't used yet. So for instance, we have foo 39 and bar 012. We're going to look for, I'm talking about this 0 right here. It's the smallest index across all. We're looking for the smallest index across all entries in the dictionary. Index across all entries in the dictionary. Okay. And this would be, and then we are going to call this start. And start will eventually form part of our answer. We're going to test if start is eligible. Next, we're going to test if start is the beginning of a permutation of words. Next, we're going to remove start from the dictionary altogether. And then we're going to repeat. So the algorithm looks a bit like this. You have foo 39, bar 012. We're going to say, let's do this one. Algorithm example. I'm actually curious, for the folks who are watching this either live or afterwards in the YouTube video, I'm actually curious how useful these explanations are, because I'm starting to realize that this is a fairly complicated problem. And I want to know if my explanation is sufficient for you to follow what we're doing. Okay, so the strategy is as follows. First, step 1, find smallest index. Okay, that will be 0. Start equals 0. Okay. Step 2 check if start is the beginning of a new permutation. And so the way to do it is to say so 0 so 0, we're going to check 0, we're going to check 3. Okay, because there are 2 words total, we just check 0 and 3 and we're done. Okay, I'm thinking of a lot of things here. Actually, like a lot of things are going through my head. So one thing that's going through my head right now is that I may not have chosen the best data structure here. I want an occurrence dictionary. Okay, never mind. Let's do it this way first. So I'm going to check 3-0. Yes, this is the start of a new word. Okay, so we add our result equals to 0. Okay, so we add 0 to our result. Now we remove 0, which means bar is 12, foo is 3 and 9. We find the smallest index. Now the smallest index will be 3. Okay, now start is 3. Then we check if start is the beginning of a new. Start equals 3. And then we check is start the beginning of a new sequence. So we check 3 plus length. Length is 3. So 3 plus length is 6. Is there something at 6 in bar? Nope, there's no bar at 6. This is not the beginning of a new permutation. So because start is now not this start equals 3 is not the beginning of new permutation, we don't do anything. So we go back and we remove start again. So now we have 9 and 12, and we do the same thing. Now start is 9. This is the beginning, so it's 9 and 12. Yeah, so that's the strategy. That's what we're gonna do. And as I work through this, I'm starting, the gears are starting to grind a little bit. I'm realizing I'm always looking for the next smallest thing in the dictionary. Well, that's really annoying to find in the dictionary. Okay, so whenever you think of your algorithm and data structures sort of go hand in hand. As you think of your algorithm, you should think about what are the best data structures to use for this algorithm. All right. So in this case, because I see myself scanning from left to right, and every time I'm looking the whole dictionary, we're looking at this whole dictionary and saying, hey, I need, I need the next smallest thing. That's kind of annoying. That is kind of annoying. So instead of saying, making a dictionary of words, the keys, where the keys are words and the entry are the indices, I am going to turn it around. I'm going to create a different dictionary. And the dictionary looks like this. It's going to be keyed on the indexes. I'm going to say 0, bar. This is going to be funky. 3 will be foo. 9 will be foo. And then 12 will be bar. This is how I'm going to build the array. So the reason why I need a dictionary here is because I'm thinking ahead a little bit. So you might look at this and think, okay, well, isn't it simpler to just make this an array? Or a list. We just drop this foo and bar. We just make these numbers in an array. But unfortunately, you can't actually do that because we can't actually do that We can't actually do that, unfortunately. We can't do that, unfortunately, because there are these like degenerate cases where it's ba ba or like fu fu, you know, where you have words like fu ba, right? And then this will be the start of fu. This 9 here will be the start of fu and also the start of fu ba. So these are kind of annoying. These are slightly degenerate cases. Okay, so what else am I thinking? So again, it's always good to start with a strategy first. Try to work it out and decide if you want to change tack halfway. So as I'm doing this, I'm thinking, actually, you know what? I may not even need a dictionary at all. Why not just maintain Yeah, I may not actually need a dictionary at all. Why not just maintain things that are eligible? Why not just maintain okay, this is what I'm thinking of. This is like algorithm 2. So I have one algorithm. Okay, let me just complete my thoughts here. So this is algorithm 1 example. This is try number 1, right? So first I started with this. I decided, maybe not. I'll do this instead. So this helps me do my algorithm. This same algorithm here, but do it faster, right? So find next smallest index. So first smallest index is 0 because all these things we can actually sort. We can sort these keys since it's a dictionary. We can sort the keys, and we'll sort the keys and say, okay, 0. What we got? We got bar, 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 or we got like bar. Okay. And then we'll check if 0 is the start of a new permutation. So 0, 3 it is. Well, that's great. And then we toss it away. And we go to the next one. Yep. So I think this. Just give me a second. I'm checking my text messages. Oh. Okay. So fu fu ba ba. Okay. I think maybe what. Okay. How about. Maybe I'll keep both. Maybe I'll keep both just to make my life easier. And I might end up throwing both away. I'm not sure yet. So I have occurrences. Yeah. So I have occurrences, which is a dictionary from. So this is occurrences. I'm going to make another dictionary, and I'm going to call it. Let's call it sequences. Sequences is too ordered. Let's call it ordered. I don't want to use words like indices because it's let's call it sorted. Okay, so sorted. This is okay. So occurrences is very simple. Occurrences word is just indices. Indices will be this. And now I'm going to expand it. I have sorted. Sorted IDX. Plus append. Append word. Okay. if ADX not in sorted IDX equals. Okay, cool. So now this will give us both occurrences, which is a mapping from the word to where they appear, and sorted, which is a mapping from where they appear, the index where they appear, indices to words. It's kind of funky. It is kind of funky. Okay. Now, this makes finding the smallest index across all entries really easy. So this is the reason why we need multiple data structures. Now, if you're still you know, a lot of beginning programmers will say, hey, this is kind of weird, right? Why do you put the same data into two different representations? This and this essentially contains identical information. Why do I need two of them? Well, I need two of them because one of them is easier for doing this, and the other is for doing this, finding the smallest index, and the other is easier for doing these occurrences. Test is start is the beginning of a new permutation of words, I think. But let's find out. Maybe we don't need occurrences. I think we might not need occurrences. We might just need this sorted. Okay, so find the smallest index across all entries in the dictionary. Well, basically what we're doing is we're doing for a key in sorted. This is going to be the next smallest thing in the whole dictionary, right? This will be step 1. For key in sorted, we're going to start from 0 first, and then we want to check if oh no, not key in sorted, dot keys. Oh, we actually don't need to do this, right? I think we can do this. I don't remember exactly. You know what? Actually, since we are going to spend a lot of time here, let's open up our trusty Python tutor. Yeah, you know what? One day I will get a paid version for this. So we're not all struggling. We're not all slumming it out. Okay. You know what? Let's run this first. Let's run this first to make sure we have sorted and occurrences right. So let's visualize execution. Indices. Yeah, visualize execution. Close. List is not defined. Man. And this should not be a self because it's not in a class. Okay. Find all is not. Okay, let's copy find all. Yeah, we didn't even test find all. So in sorted. Not index in sorted. Oh. Let's use another this is a special keyword. Let's just call it lookup. Visualize execution. Okay. Let's see what happens. Okay, cool. So let's see what happens. So let's jump all the way to the end. We run all the way to the end. Okay, words is full bar. Occurrences is full bar. Full is 3 and 9. Full is 3 and 9, and bar. What is bar 12? That's weird. Bar should be 9 and 12. Bar should be 0 and 12. Okay. That's fine. Bar should be 0 and 12. So we have 3, 9, and 12. 3, 9, 12. Okay. So, again, this is almost right. It should be 0 bar, 3 full, 9 full. 9 is full. This one right here, 9 is full. And then 12 is bar. So we're missing the 0. I think the problem is with this find all. Find all is not doing a good job. Okay, and I already see what the problem is. It's doing previous index plus 1 here. It should do this. Oh, sorry, plus 1. So because I start from previous index plus 1, it's going to start searching from 1 instead of from 0. So this should work. Previous index equals in the IDX plus 1. So visualize execution. Okay, so now it's correct. So full will give you 3 and 9. Bar gives you 0 and 12. And you have 0, 3, 9, and 12. Full, bar, full. Okay, so notice that this is not in order. But that's fine. That's fine. Okay, cool. So this part is correct. So we have our occurrences and we have our lookups. We have lookups. So for each, can I do like this? I don't remember. Python for loop dictionary. Can I do like a key value pair? Distinct. Okay. Can I do a key value pair? Oh no. It just, so when I do distinct.values, distinct.keys, this would only get values. Okay. So I guess I can't do that. I was actually thinking of something like this. In lookup. Yeah, I was thinking of something like this, but I guess you can't do that. So just do IDX equals to, not to reuse this name. I'm going to use words with 2 S's. I feel like this is really annoying. But we'll fix it later. So words equals to lookup IDX. Okay, and this words is guaranteed never to be empty. It's never going to be empty. Okay, cool. And so this would basically So lookup looks like this, right? Lookup looks something like this. So this would basically go through 39303912 blah blah blah. I don't remember if this IDX is sorted. If it's not sorted, then we have to do something about it. We can do like dot keys dot sort. Right? We can do something like this. But we'll check. We'll find out. We'll find out if this is okay. Words equals sorted. Okay. So let's assume that words is a single thing first. Okay, and this is not the right way to do it, but we'll fix it later. Let's assume that word is a single thing first, because this makes it easier to explain the simple examples. So let's say word is a simple thing. Our job here is to check if IDX is the beginning of a permutation. We want to check if IDX is the beginning of permutation. And to do this, essentially what we want to do is to go is to look at the other. So this is, oh, okay. Is to check if the beginning of a permutation. So what we want to do is we want to check we want to take IDX. To do this, we check IDX plus length times 2 up to IDX plus length times n, where n is the number of words. Actually times n minus 1. Where n is the number of words. And we want to check that this, oh yeah, and we check that these all appear here. So we go 0, we go 3, because there's just 2 of them. And we want to make sure that they contain distinct words. Okay. So to do this, I'm going to write a for loop first, and we'll see what we want to do. Okay. So this might get a little bit tricky. For I in range n multiple. Oh, actually I shouldn't even do this. X in range IDX. We're gonna use sort of like fancy range syntax. We're gonna say we're gonna start from IDX, and we are going to do n, where n, let me see, n equals length of words. That's how many words we have. Length, and we'll add 3 each time. Actually, we can do a check here. So basically we're going to say, so basically IDX will start from 0, okay, and then this for loop here will go from 0, you go 3, you go 9, you go 12, blah blah blah, for n times. Now we want to make sure that we're not going past the length of the word, which actually we don't care, because we don't care that we go past the length of the word, because we're not actually doing some sort of array. We're just looking at dictionary lookup. Okay, cool. Okay, so the idea here is we want to have Okay, so let's again do it the wrong way first. We're gonna do it wrong way first. So the thing we're trying to do is the following. Okay, we're gonna do it the wrong way first because the wrong way is easier to explain. Okay. So the substring at next IDX. Let's just call it start because that's the word we use, and then we can use a smaller start 0. So we can call this IDX equals to start. IDX. Let me see. Equals to lookup IDX. Okay, so we're gonna start from 0. Okay, so I'll start at 0, and we're gonna start from 0 and say, okay, well, we're gonna check. We're gonna check if this is the start of a new permutation. So words at IDX. Again, right now, what we're going to do, we're going to assume that it's not words, it's just one word. We're going to assume that every index matches to a single word. This is not correct because words can contain other words. Words can duplicate, in which case, all hell breaks loose. We're not going to consider that first. We're going to do the following. So words at IDX equals lookup IDX. We are going to take that word and we're going to stick it into a if words at IDX dot empty, then so this thing is, let's put this in a separate function. You know what? Check start valid. So we have start length This is more trouble than it's worth. If words.idx is empty, so for instance, there's no 0, we start from 0, there's no 3, then of course that's not gonna work. Then we can just break right away. If not, then we have a perm equals. This may not be the best way to do it. We might try this problem again the next time we stream, but we have a faster way of doing things. The faster way takes more memory. But it's actually easier. I think. I'm not sure. Okay. So words at IDX is empty. Let me see. Current perm. We just need something that's valid, right? So perm starts from nothing. Okay. Okay, let's do it the wrong way first. Let's do it the wrong way. The thing that will work for this example, but may break on some more perverse cases, more degenerate cases. So perm starts from empty, and the idea is we're gonna stick things into perm, right? Otherwise, perm dot append words 0. Okay, we're gonna stick things into perm. All right. If okay, we're gonna do it the wrong way first. If perm dot find Python list contains we can just use in, right? I think you can just use in. If word 0 in perm valid equals to false, break. Okay. Okay, I think this will work. Results dot append start. Okay, cool. I think this will work. I'm not sure. I think this will work. I hope this is not too long. Hope I'm not triggering the word limit. List has no object empty. Is there no object empty? So I have to do this. Length of word equals 0. Actually, I can do like not. Okay, cool. So, okay, cool. Let's jump right here. Let's jump right to line number 30. Okay, so line number 30, we have created our words, our occurrences, and our lookup. I don't think we end up using occurrences, but it's good to have it. Lookup is 0, 3, 9, and 12. 0 will be man. 0 is bar. 3 is foo. 9 is foo, and 12 is bar. Okay, cool. Okay, so the next thing, let's step through this properly. So valid equals to true. So start equals to 3. Oh god, this doesn't work. Already there's a bug. So we can't do this. So remember I said we need to sort this, right? I think it's like this. Oh no, it's dot sort. Remember what I was talking about just now? Where I said I need these keys to be sorted. I need this to start from the smallest number. So going back to here, I need start to start from 0. It's starting from 3. Because the keys in the index is not guaranteed to be sorted in any way. Okay, cool. So has no sort. How do you sort? Python dictionary sort keys. No, not sort keys by value. Sort keys numerically. Yeah. Okay. All right. Let's do it this way. Okay. So I need, this is so weird. Start word in sorted. Ah, I see. Lookup.items. So instead of doing lookup.keys and or lookup.values, I do lookup for .items, which will give me both start and word. And because, okay, and then I sort them before starting it. Okay, so this will do what I want. I did not know this before, so this is a good place to start. Invalid syntax. Run it. Close. So we are here. Okay, cool. So back to regular programming. So start is 0. Perfect. We want this 0 right here. Okay, word is bar. Okay. Okay, we're gonna edit this a little bit. We're gonna make it even more wrong, but that's fine. Wait, yeah, word. Oh, this is words. Oh, we don't even need this. We just need the key. Because we never actually end up using words. We're gonna start again from here. Okay. Cool. We don't have to care what words is. Okay, so let's come back to here. Sorry for all the jumping around. You guys should definitely let me know in the chat if this jumping around is making it difficult to follow. Okay, let me know in the chat or in the comments if this jumping around is making it hard to follow. As it stands, I like to do my programming. I like to solve the problems while at the same time as you. So I'm looking at all these problems for the very first time in my life. So I'm trying to figure them out as I'm talking. So that means that what I say, my words follow my thoughts, and my thoughts do jump around, and that's going to be how it is. Okay, so valid is true. Word, I don't care. I don't actually care what word is. Okay, we're gonna go next. So perm is forgot what perm is. Oh, perm is nothing. That's fine. So idx equals start, range n. So n is equals to 2, length is equals to 3. idx is equals first to start, which is 0. So idx is 0. Okay, so words at idx. So words at idx is bar. So words at idx is bar. Because we are looking at bar foo, the foo bar man. So words at idx is bar. And so we are going to check. Okay, let's go next. If not works at IVX, valid equals to false. Yeah, nope, this is fine. So words dot in perm. So perm currently is empty. That's true. So words perm. Okay, cool. That's great. And now we go to the next one. If IDX in range, blah. So now IDX should be this is a little bit annoying. Oh, okay. Yeah. So this shouldn't be n. I want it to be start plus length times 2. So this should not be n. This should be like Yeah. Let me see. What should it is? Do some mathematics here. So it's start plus n times length. I think this is it. Plus 1. Yeah. Wait, what? Key values, key error 6. Oh, okay. If I need to check the key error first. If not IDX in lookup. I need to check this key errors. Words.index. Words at index 0 in perm. Okay. I think this is correct. Let's try it again. So come back to here. We do next. Okay. Take this out. Next, next, next. So, alright. IDX is 0. Start equals to 0. IDX is 0. So at 0 we have bar. Okay, that's great. So we'll add bar. In perm is not in perm, so add bar to perm. So now bar contains perm. Perm contains bar. Perm contains bar. Okay. And now we do this again. It's not. And then IDX, words at IDX lookup is now full. Okay. It's a pen. Yep. So that's valid. Okay, that's perfect. And so now perm has, the permutation is bar and full, right? That's our permutation. And that's great because that means that, wait, if not IDX, what is IDX? IDX 6. Why is IDX 6? Oh, okay. So it shouldn't be plus 1 times length. Okay, cool. Let's try it again. Off by 1 errors. Off by 1 errors always occur. This is how it is. Okay, third time's the charm. Okay, so permutation perm is empty. So basically what we're doing is that we're saying, okay, we're gonna start from start. Start is 0. We want to see is 0 the start of a valid permutation. And so what we do is we're going to start from IDX. This code here, line 36 to line 46. This code here, okay, this part checks if start check if start is the beginning of a valid permutation. Okay, we're trying to check if start is the beginning of a word that we want. This is what this part is doing. And the way it does this check is there's a for loop that checks 0 start is a start plus length, start plus 2 length, dot. And it's going to check that at each of these indexes, each of these indices, there is a word that we can there is a word that we can use. Okay, so I hope this helps you see why lookup is a better data structure than occurrences. Imagine having to do these things with occurrences. This would be such a pain if you had to do it with occurrences. But lookup actually does well. Oh, oops. Lookup actually does this fairly well. Does the job fairly well. Okay. I'm pretty sure this should work right now. Next. Okay. So next. Okay. So IDX. So IDX is 0. IDX is 3. IDX is 3 right now. IDX is 3. 3 is full. So our permutation is bar. Perm, you see, goes to bar. Okay. Now we have bar at start. And then full at start plus 3. Nope, it's not in perm. So perm at, okay. And valid. Valid is true. So append start. So results. Wait, result should append start. What is result? Result will be 0. Yeah, awesome. So 0 is one of our solutions. And then we just go next. Wait, IDX is 6 now. So valid is false. So this is for start 3. So start 3 is here. Start 3 is here. So start 3 has full, but the next word after full is the. So start is 3, and then this is 6. So we're gonna check 3 and 6. 6 actually is it doesn't occur in lookup at all, because the is not a word in full and bar. So you see, lookup doesn't have index is not in lookup, so that's why it sort of breaks. Okay, now it goes back to start. Now next start is 9, and this should pass. So at 9, so perm is empty. IDX starts from 9 first, yeah. If not IDX in lookup, IDX is in lookup. Words at IDX. Word at index. Word at index is full. Okay. Perm dot at full. So you see, this is perm. Yeah, this is full. Okay. So perm now adds bar. So full bar. Okay. So now valid is also valid. So 9 should also go into results. So results is now 0 and 9. And I think it goes to 12, and 12 is not valid. Now in IDX, start is 12. IDX is 12, that's fine. But the next IDX is 15. So 15 is passed. Oh, it's actually not passed. 15 is this one, is this M here. So 12 is here, 15 is here, 12 is this bar, and then 15 is this man. Because obviously 15 is not the start of a word we recognize. 15 is not going to be in lookup. You see how 15 is not in lookup? It breaks. It's invalid. And then I think this is it. So it'll return. Oh, it doesn't show the answer. Okay, cool. So this works with caveats. Okay? There are... Okay, let's copy this back to our work here first. Do we need to fix this? Okay, this is fine. Let's copy our work back into LeetCode so we can save it. I think we're gonna stop here for today. And this actually works for a very specific kind of problem. Okay, so this actually works for the first example, but it doesn't work in general. It doesn't work in general because it's gonna fail for a few things. One is I think it's gonna fail for this, and it's definitely gonna fail for this. Actually, I don't know. Will it fail for this? I'm not sure. It will definitely 100% fail when you have things like this, right? So foo is 039. So if you do the lookup, we have 0, which goes to foo. We have 3 that goes to foo and foo bar. Okay, so we're not talked about these kind of degenerate cases. We've not talked about this case. This case is very annoying, right? This edge case. So we've created a program that works if there are 0 edge cases. We've created a very simplistic program that works. Okay, so let's run this. I'm curious if it's actually going to work in. It's going to work for case 1 for sure. Oh yeah, this is annoying. So in I think different versions of Python, you can actually make this like a local function. But I don't know you can do it in this version of Python. So you do that using an annotation. So you wait. Why is case 1 wrong? Case 2 is right. Case 1 should be right. Case 1 is the one we tested. Foo bar foo the foo bar man. Oh, that's interesting. So this is wrong. This is right. Oh no. I see. So we didn't return. We did not return result. Okay, so case 1 should be right. Case 2, I think is also right. I'm not sure. Okay, case 3 is also right. Wow. Nice. But it's not going to be right in general. If you submit this, there will be wrong answers. So we have created something that works except for edge cases. I'm going to write down the edge cases where this doesn't work. To do for next time. Bug 1 does not work when there are multiple words. Yeah, you see, it works for 160 out of 179. This is actually pretty good. But it doesn't work for this one. It doesn't work when there are multiple words. Multiple duplicate words. And bug 2 does not work when words overlap or contain each other, which I guess is just a special case. Like this bug 1 is a special case of bug 2. Yeah. So we sort of got it. So I think we did good, right? It doesn't work when there are things like these. So it works out for 160 out of 179. It doesn't work when the words duplicate. When they're duplicate words. I'll put there. It should be 8. Yeah, because the way we test for perm, right? The way we do tests for perm is, let's say we're 8, 0, 4, 8, we're here. The way we test for perm is we're saying, okay, good, we have good, perfect. Now do we have the other good? Well, because our perm already contains good, the second time we see the second good, this second good here, we say words at IDX 0 is in perm. Well, sucks. That's too bad. We're gonna fail right away. Okay, so that's the problem that we have. That's the problem we have. We have to fix this. And part of fixing this involves making this not square bracket 0. Because right now we always assume that words at IDX contain only one thing. That's not right. We need words at IDX to contain different things. And we also need to like fiddle around to make it a little bit better. But either way, I think this is a good stopping point for today. Get in the comments and let me know if this explanation is actually useful to you. Yeah, today's problem is a little bit more complicated. And the next time we're going to continue with this problem and finish it up. And that's